Well, see, we have developed the idea what is delta H and what is delta E for any chemical reaction. Now see how to determine and calculate this delta H for chemical reactions, how to write the thermochemical equation, and what is the meaning of different parameters used in the thermochemical equation. See, whenever you are writing any thermochemical equation, some points should be, keep in your mind that you have to write the reactant and product not only in the bare form, but you should specify their physical states as well, because this is the very important feature of a thermochemical reaction, that you have to mention their physical state, right? Suppose that any solid, you are mentioning solid, and if that substance has some allotropic form, then you have to mention allotropic form, precisely mention the allotropic form, otherwise your calculation will be wrong. So suppose that I am writing one equation, Fe2O3, Fe2O3. Usually in casual approach we simply write Fe2O3 plus hydrogen gives Fe plus H2O, like that we simply writing in the chemical calculations and in other chapters. But here it is not workable. Here you should mention the phase, means state of the substance, as well as if some allotropic form is there, then you have to clearly mention which allotropic form you are taking here in this particular reaction. So Fe2O3 solid plus 3H2 gas gives 2Fe solid plus 3H2O liquid. 3H2O liquid, right? So this is a we can say ideal thermochemical equation. Now, what is the meaning of this 3 here, this 2 here, and this 3 here, and 1 here? So they represents basically moles. These stoichiometric coefficient, they represents moles, right? Not molecule. Never say this is molecule, right? Not molecule. Right? And suppose that delta H of this reaction, why I am talking about delta, as you know, like internal energy, we can measure the difference, right? Reference is same, 0 Kelvin. So we always prefer to measure the reference, difference, not the absolute value, right? Like internal energy. So delta and as per the IUPAC nomenclature, you have to put the process with delta after H. After that you have to write H. So delta RXN, in short form you can write R and H, right? Although you can write delta H reaction in casual approach, many people are writing delta H reaction or whatsoever specific reaction like combustion, like formation, like neutralization. So people have tendency to write delta H combustion. But as per IUPAC recommendation, the process should be written with delta after that H. So if this is given minus 33.3 kilojoules per mole, right? So what is the meaning of this? How to interpret this representation in any thermochemical equation? First representation, see this negative sign, what is written here. Negative sign means energy, and basically which energy? Heat energy. Energy coming out or going from system to surrounding, going to surrounding from system. So energy means heat energy going to surrounding, going to surrounding from system, from system, right? This negative sign. Clear to everybody? Hmm? And such type of reactions are said to be what? Exothermic. Exothermic, right? Clear? And one more thing we can see, represent this. One more way we can represent this, if we mark this as a reactant, or these are the reactants, basically both are reactant, and this we can mark what? Product. So in the energy profile, we can show this terminology. So I am not representing this both the products differently. I am collectively taking that energy of this product. One more way to represent this. This is energy, and this is progress of reaction. Progress of reaction. So here we can represent like this. Here reactants are here, and products are here. Means product have this average energy, and reactants have this average energy. Means once this data is given in any question, you can interpret this like this also, that the average energy, sum of average energy, because this is not one product, so you have to write like this: the sum of average energy of products is less than sum of average energy of reactants. By what factor? By this factor, 33.3 kilojoules per mole. Don't, at this time, don't say minus, because already you have explained that energy of product is less. So what other meaning of such representations is the sum of, because I am writing with respect to this my reference reaction, the sum of energy of products is less than the sum of energy of reactants. Clear to everybody? How much quantity? How much quantity is less? Less by 33.3. So we can say that delta H of reaction, we can say that delta H of any reaction is the sum of average energy, because all of you are knowing that this is from here to here, this is called average energy. Average energy of products minus sum of average energy of reactants. Clear to everybody? Hmm? You can write this. Okay. So this is another meaning of this representation, that what is the meaning of this? So here in the graph you can represent that this difference is basically delta H of reaction, and this is equal to 33.3 minus, you can put here, kilojoules per mole. So this is another way of representation of what this data, and for your better understanding, what is the meaning of this, right? That the energy of product is less than the energy of reactants. And if you follow the principle of gradient, general principle of gradient or potential, then you can say, okay, whenever the energy of product is less than the energy of reactant, means the reaction is exothermic, then this reaction will occur spontaneously. No external help is required to proceed this reaction in the forward direction. Yes, we can say this, that if the energy of product is less than the energy of reactant, so as per the simple concept of mechanical principle of energy gradient, that the flow of energy is always takes place, or flow of any process always takes place from high energy to low energy. So as per this simple rule, such type of reactions should be spontaneous. Now I am creating one more problem for you people, and you have to think on this problem seriously, because in next few lectures I am going to introduce another thermodynamic function, and basically the cause of that introduction of that thermodynamic function is started from here. So in many cases, in many cases, such type of reactions, such type of chemical reactions, I mean, which type of chemical reactions? Reactions in which the energy of product is less than the energy of reactant, means reactions are exothermic. So such type of reactions are spontaneous, right? I am telling you, in many cases, not in all cases. Not in all cases means that it is not necessary that if the reaction is exothermic, now I am using single word exothermic, now you understood, okay, the energy of product is less than the energy of reactant. I am not going to repeat every time. So not in all cases, if reaction is exothermic, then it is what is spontaneous, or endothermic, then this reaction will not spontaneous. means apart from energy, some other driving force is also there for chemical reactions, right? For the spontaneity of chemical reactions, some other driving force is also there in the system which derives the reaction in a particular direction. And you know that function is known as entropy. So energy, sole factor, energy is not the sole factor which governs the chemical reactions. Okay, it is true that in many cases, so I am writing this statement that in many cases, not in all cases, in many cases, in many cases, exothermic reaction, exothermic reactions means delta H negative, delta H negative will occur spontaneously, spontaneously, right? While endothermic reactions for which delta H is positive will not, will not, right? But 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 not always. Remember this, but not always, right? Means not every time that endothermic reaction will be non-spontaneous and exothermic reaction is spontaneous. Some other factors are also important here, which controls the direction of the reaction, which controls the spontaneity of the reaction. But next few lecture we will develop the concept of this enthalpy. After that, I will talk about this next thermodynamic function, which is also play a very important role to explain the spontaneity of chemical reaction. But remember, mechanical processes. Remember very carefully, mechanical processes. To explain the mechanical processes, only energy is sufficient tool, or energy is sufficient factor. Entropy is not required. But for chemists, it is very important. But for chemists, it is very, very important. Clear to everybody? Okay. So, this exothermic reaction, now you understood what is exothermic reaction, what is endothermic reaction. Now I am taking another feature. See, whatsoever the value of this delta H represents along with this unit, what is the meaning of this per mole here? This is very important point. Many of you are confused. Per mole of what? Per mole of Fe2O3? No. Per mole of hydrogen? Answer is no. So what is the meaning of this per mole? See, whatsoever the value of delta H given, that tells the energy change for the reaction as written in the balanced form. It is not allowed in thermochemistry that you are going to divide or multiply any equation. If you divide or multiply any equation, delta H accordingly will change. As you know, this is extensive property. So if you divide, multiply. So this per mole, basically per mole here, it is the per mole of reaction as written. So be careful whenever examiner has given you any thermochemical equation and it is asking, okay, calculate delta H per mole. So don't divide, don't multiply that equation with any factor. Otherwise, your answer will be wrong. Until or unless it is not asked that for this given reaction is this enthalpy change, and for particular reactant that 1 mole or 2 mole, what should be the change, then accordingly as per the situation you can manipulate. But whatsoever here value unit is given for an enthalpy change, that is per mole of reaction as written, right? So the unit, next point I am taking, the unit of delta H is kilojoules per mole or joules per mole, right? And the meaning of per mole is here kilojoules per mole or joules per mole, uh, as written, as the reaction written, as the reaction written, right? So this is the per mole as the reaction written. This is not per mole of this I mean Fe2O3 or per mole of hydrogen or per mole of iron or per mole of water. This is for 1 mole of Fe2O3 for involving 3 moles of hydrogen for getting 2 moles of iron and 3 moles of water. So this is the meaning. So this is the convention. This is the method to write the unit for delta H, unit of delta H for any given reaction. Suppose that if you divide this equation with any factor, suppose that you are dividing this, suppose that you are dividing this equation with the factor 2, then what will happen? So 1 by 2 Fe2O3 solid plus 3 by 2 hydrogen gas will give Fe solid plus 3 by 2 H2O liquid. So delta H for this reaction, or delta H dash for this reaction, is equal to delta H of above reaction by 2. This is 1, this is 1, right? 1. So this is equal to minus 33.3 by 2, and again you are writing kilojoules per mole. What you are writing? Kilojoules per mole. This time also you have to use per mole, right? So if you divide or multiply any equation with any factor, delta H accordingly will change. Suppose that you reverse this reaction, then what will happen? So if you reverse this reaction and writing like Fe I am reversing the first reaction basically. 2Fe solid plus 3H2O liquid and Fe2O3 solid plus 3H2 gas. If you reverse this, then delta H of reaction double dash we can take, or 2 3 we can do 2 and 3. This is equal to minus of delta H1. So this is equal to minus of minus 33.3 kilojoules per mole. This time also you have to write kilojoules per mole, right? So this is equal to 33.3 kilojoules per mole. So this reaction becomes endothermic. Endothermic means if you reverse the direction of any reaction, delta H, sign of delta H will change. So you can say that all algebraic rules are applicable when you are manipulating this thermochemical equation, right? All algebraic rules are applicable when you are this manipulating the thermochemical equation. Clear to everybody? Okay, good. So this is the importance, and this is the feature of thermochemical equation and understanding of this enthalpy of reaction. So hopefully all of you are clear that what is the meaning of this unit kilojoules per mole. This per mole is not any one individual reactant or product here. This is as per mole of the reaction, as written the reaction, right? What is the meaning of this negative, and what is the meaning of this exothermic reaction, that energy of product and reactant, what is the relation. So I think everything is clear. And one more thing I have introduced here is spontaneity, condition of spontaneity. So usually many cases exothermic reactions are spontaneous but not always, right? So this is the feature of or importance of any thermochemical equation. Okay. Now see different terminology here. I have mentioned what are enthalpy change, right? Enthalpy change, symbol for this is delta H of reaction, and standard enthalpy change. So now we are trying to standardize the condition under which the enthalpy of any reaction is measured, and reference scale of enthalpy and other thermodynamic functions. So first I am going to differentiate here between delta H and delta H naught, right? Another term introduced here, delta H naught. So basically delta H and delta H naught. Delta H is defined at, measured and defined at any, listen carefully, at any constant temperature T and pressure. So if you determine heat change or energy change in any reaction at any constant temperature and pressure, then this is called delta H. What is this delta H naught? Basically this naught term, this is used for uh, or this naught means in whole physical chemistry, in whole chemistry, this means 1 bar. This means 1 bar. So whenever this subscript you are finding anywhere in the chemistry, so it means it is 1 bar, right? And constant temperature, constant temperature. Many many people are doing mistake here, that they always take this constant temperature is 298.15 Kelvin, but this is not true. See here, this means 1 bar, clearly 1 bar, not beyond 1 bar, any pressure is not acceptable. Means except 1 bar, no pressure is acceptable for the measurement of this. But and constant temperature, T should be constant, but not mandatory that 298.15 Kelvin. Okay, if temperature is not mentioned anywhere, then default is 298.15 Kelvin. But default means not always. So delta H naught is basically um, named as standard enthalpy change, and similarly what I am defining here for this enthalpy, it is true for every thermodynamic function and even true for whole chemistry anywhere. So and constant temperature T, and if temperature is not mentioned, if T is not mentioned, then it is 298.15 Kelvin, right? So this is important. Now try to understand. Suppose that a reaction is given like this: X gives Y, and delta H or heat change, heat change is given is equal to minus 20 kilojoules per mole, right? At 500 Kelvin and 1 bar. So what is this? What is this value? This is delta H naught, or it is delta H, right? Suppose that the question is given like this, that the heat change for this reaction, it is given minus 20 kilojoule at 500 Kelvin and 1 bar. So what is this? So dear students, this is delta H naught. This is not delta H for the reaction, because for standard state or standard enthalpy change, the only requirement is 1 bar pressure and constant temperature, not necessarily 298.15 Kelvin. So at 500 Kelvin, it is a constant temperature and 1 bar pressure. This is a mandatory condition. So this is delta H naught, not delta H. Similarly, if X gives Y, and this time heat change is equal to minus 10 kilojoules per mole at 298.15 Kelvin and 0.5 bar, right? So what is this? This is delta H or delta H naught. So this time this is delta H, not delta H naught. This is delta H. Because this time pressure is not 1 bar. Clear? Clear? Now take one more example. X gives Y. X gives Y. And this time heat change is given minus 12 kilojoules per mole at 298.15 Kelvin and 1 bar. So what is this value? This is delta H or delta H naught. So this time this is delta H naught, not delta H, because 1 bar pressure is fixed here. So this is not delta H, this is delta H naught. So in your table, in your book, what appendix you have in the NCERT book, thermodynamic data are given. So all those data are given at 298 Kelvin and 1 bar, but don't confuse that at only 298 Kelvin, this is called delta H. So if somebody asks, okay, for any one reaction, can we have two different values of delta H naught, two different values of standard enthalpy change? Your answer is yes. Means for a single reaction, we may have 2 or 3 or more delta H naught values. Definitely all those values are different if you are taking at different temperature. But they are said to be delta H naught, not delta H. So don't be, strict about temperature. Temperature should be constant, and in the same manner, standard state of any substance is also defined, and this is given in your NCERT book, Thermodynamics chapter, and in the bold letters they have written this statement, but people are not bothered about to study or go through the this NCERT book. They have very beautifully written this and very clearly. Standard state of any matter. Standard, they have written like this: standard state of any matter is defined at 1 bar pressure and at constant temperature. They have mentioned constant pressure 1 bar, but they have not mentioned constant temperature to 98.15 Kelvin. They have only written constant temperature, right? It could be anything, any temperature, depending on your experiment, requirement of your experiment, right? So not necessary that every time you should measure the standard state or standard functions. And now the same meaning for all standard thermodynamic function like delta E naught, delta H naught, delta S naught or S naught. Why I have written S naught and delta S naught? Because absolute value of entropy can be measured, right? And delta G naught, all they are standard function at 1 bar and constant temperature, not necessarily 298. Clear? So all thermodynamic functions you can write like this, and standard state also defined. Standard state is defined of any substance, of any substance in pure form and if more than one allotropes are there, then most stable allotrop. Most stable allotrop, right? At constant pressure 1 bar, constant pressure 1 bar, and at constant temperature, right? Not necessarily 298 Kelvin. Constant temperature is requirement, not 298.15 Kelvin is requirement. Clear to everybody? Okay. And now, for every element, for this is very important point, for every element in its most stable form, in its most stable form at 1 bar, and 298.15 Kelvin or any constant temperature, right? 1 bar, because in your syllabus this is what default, but concept should be, your concept should be clear. So at 1 bar and 298.15 Kelvin, delta H bar we can write here per mole, basically naught is equal to 0. This is the, reference scale. Similarly, delta E naught per mole, this is also equal to 0. Delta G naught is also equal to 0. But S naught or delta S naught per mole, you can take this. This is not equal to 0. Right? See, most stable form means the formation of element in most stable form, delta H, delta E. This is a convention basically. So we are taking this is equal to 0 at what? This reference point. Okay. So for example, you should see through example delta H naught. Suppose that for hydrogen we are talking. So what is the most stable form of hydrogen? The most stable form of hydrogen is hydrogen gas. So for this, this is equal to 0. Similarly, delta H naught for carbon. So for carbon, which allotrop is the most stable form? Graphite. So carbon graphite, this is equal to 0. Similarly, all these functions are also 0, but entropy is not 0, right? Entropy is not 0. This is not 0 for diamond or for other allotrop. Clear? See, one exception is there of this. What is the exception? The exception is phosphorus. P4 white. This is the thermodynamic reference. So delta H not for P4 white is equal to 0. But the most stable allotrop of phosphorus is most stable allotrop of P4 is P4 black. So P4 black is the most stable allotrop of phosphorus, but for P4 white thermodynamic reference we have taken P4 white. This is the only exception. And for rest of the elements, for rest of the compounds, molecules, whatsoever, delta H formation is 0 for most stable allotrop. You can survey the appendix which is given in your NCERT book. You will get the complete list, and you can see for those species this delta H naught or delta G naught is 0 given. That is the reference, thermodynamic reference, right? That in thermochemical reaction we are taking that a thermodynamic reference. Clear to everybody? Okay. So this we can write here that every compound in their standard state, for every element in their standard state in pure form, this all these functions are 0, right? One more thing I would like to mention here, that for H plus aqueous, this is again convention, this delta E naught is equal to 0, delta H naught is also 0, delta G naught is also 0, and delta S naught or S naught, what is this? Entropy. See, non-zero entropy here for all other elements, for every element in their most stable form, this is not 0. But remember, dear students, here this is also 0. It is a convention. We are taking this 0. It is a reference basically. So to measure the entropy of ions, H plus is the reference. So when you are, go through your table of this thermodynamic data, which is appended in the last of, in the end of your NCERT book, you will find that, okay, for some of ions, entropy change is negative given. So what is the meaning of entropy change negative? Probability cannot be negative. Entropy you can link with the probability in mathematics. So it cannot be negative. But remember, if negative entropy change is mentioned for any ion, it means the entropy of that ion is less than the entropy of H plus. So if the entropy change delta S naught for any ion, suppose that A plus aqueous ion, it is negative, some negative value, suppose that X joules per Kelvin per mole. So what does it means? It means the entropy of means the entropy of A plus aqueous is less than entropy of H plus aqueous. And if for any ion entropy change is positive, means that ion have more entropy than H plus. So hopefully all of you are clear in this regard. So this is also a very important point. This is very important point. Everybody should carefully note down. This is very important. And obviously this is also important because this is exception. So exceptions are always important, right? So this is the meaning of standard thermodynamic function versus thermodynamic functions. So this for every element you have to take this delta H naught, delta E naught, delta G naught is equal to 0 under standard conditions. And what is the meaning of standard condition? I have already explained clearly. Okay, so this is all about standard function and standard thermodynamic function. And opposite part of this you can write, if delta S not for any ion is positive, means that have more entropy than H plus, right? Well, see the measurement of enthalpy, as we know that enthalpy is a state function. So measurement of this is very easy, and the method or principle which is used to measure this enthalpy change or enthalpy, that is calorimetry. See, this is a constant pressure system I have designed. See, this is not blocked here. This is actually open. So this is in contact with the atmospheric condition. So in this chamber there is a reaction. This is liquid water you can take, and thermometer is set here to measure the temperature. Here this is the reaction vessel basically, which is under constant pressure, and this is adiabatic wall, so that heat cannot be transferred from system to surrounding or from surrounding to system. So this is the simple arrangement for the measurement of this. As you know, delta our purpose is here to measure the delta H of reaction, right? And we have specified that this temperature at, because you have to define at which temperature you want to measure this delta H. So delta H of reaction we want to measure at temperature T1, at T1. So reactants we have taken at temperature T1, and products also basically we have to bring the products at the temperature T1. Suppose that if you take 298.15 Kelvin, so it is not possible that reaction will proceed at room temperature. This is not possible that the reaction proceeds at this what constant temperature 298.15 Kelvin. Okay, so what we can do, first we fix the temperature of the reactants at T1 and allow the system for heating, so that reaction at whatever temperature reaction is occurring, that is immaterial, because you know this is a state function. So suppose that at room temperature 25 degrees Celsius reaction is not happening, and it is required to heat the reaction mixture up to 800 degrees Celsius. Okay, no problem, you heat this system up to 800 degrees Celsius, and after that what will happen? Products formed, reaction completed, and then you cool down whole system to again at 25 degrees Celsius. So basically this is two-step process, because you know reactant and products both should be on the same temperature. Then only I mean you can say okay temperature is constant, because all of you are knowing that for a chemical reaction delta H is the heat energy change at constant temperature and constant pressure. So it is mandatory that reactants and products both must be on the same temperature. But in between, I mean before the formation of product, it is immaterial that how many times you are heating, and how it is immaterial that how many times you are cooling, because this is a state function and it is independent of the history of the system, independent of the path of the system, right? So for this purpose I am designing two-step. This is a two-step process. First step I am taking here. In the first step reactants, right, at T1 temperature plus this calorimeter. This calorimeter, this is also at T1 temperature, right? You know this is adiabatic process. Now convert this into the products at T2 temperature plus calorimeter at T2 temperature. All of you are getting? We have taken reactants at temperature T1. Calorimeter also obviously because this is whole one system, basically single system we are considering this. So calorimeter also at T1 temperature. Products, we have heated this system as per the requirement of the occurrence of the reaction and converted into the product and let it be at T2 temperature, right? Pressure is constant because this is open. So non-gaseous reactions you can very easily perform here, right? For gaseous reactions it is difficult. So for gaseous reaction we will determine delta E. After that indirectly we can calculate delta H, right? Now see. Second step, products at T2 temperature plus calorimeter at T2 temperature. Now we are converting this product at T1 temperature plus calorimeter at T1 temperature. Now see, we have achieved. So the process which is seems to be very simple here, that reactants at T1 and products at T1. Basically, I have break this whole process in two steps. First, and this is second step. So delta H of reaction at T1 is equal to delta H1 plus delta H2. So this is very simple because you know this is extensive property and state function, so you can very easily calculate. Now see pressure is constant. So this time this first the delta H1 is 0 here. How? Because at this situation we are assuming that adiabatic constant pressure. So adiabatic process means heat between system and surrounding. See, whatsoever is changing here, that is totally inside the system. There is no change between system and surrounding. So delta H1 is equal to 0 because delta QP is equal to 0. This is adiabatic process. So first step is adiabatic here, right? So that's why this delta H1 is 0. This is very important. Delta H1 is 0 because there is no heat change between system and surrounding. Whatsoever is process is happening, that is only inside the system. Now second step is basically cooling. So obviously this heat should be given out. So this time QP is not 0. So basically the this delta reaction H at temperature T1, this is equal to the delta H2 only, right? So basically the first step is adiabatic here, and in the second step the heat is given out. So that whatsoever heat is given out in the cooling process, That is basically here is the delta H of the reaction. Clear to everybody? Good. So delta H of this reaction is equal to basically the cooling of products from temperature T2 to T1. See, from in this step there are so many small steps may be involved. All those steps are involved here, which involves the release of energy, like resonance, like phase transition, right? So it is not, correct here to say this is only pure cooling, but we can say whatsoever all the process which involves the release of energy, not only cooling is the process which release the energy to the surrounding, but all those processes which involves the release of energy, all those are included here, right? So this is equal to H2. Hopefully this is very much clear to all of you. Why delta H1 is 0? Because there is no heat change between system and surrounding. This step is purely adiabatic, and this is not adiabatic. So there is some change between system and surrounding, heat change. So that heat change is basically H2, right? Clear to everybody? Okay, good. So delta H of reaction, this is equal to H2. Now at temperature T1, we can write here minus T1 to T2. Why I have taken minus? Because if you see the step 2, T2 to T1. So we are going T2 to T1, but see if T1, T2 are given, so I am taking from T1 to T2, so negative sign here I have put it. Cp of products, right, plus calorimeter dt, right? Cp of products plus calorimeter dt, and this is minus T1 to T2 Cp of calorimeter dt, right? And this is equal to minus of Cp calorimeter delta T, right? So this is the delta H of reaction at temperature T. See how I have written this Cp of products plus calorimeter is equal to Cp of calorimeter, because you know in most of the cases, what we are designing here, that this Cp of calorimeter, that is constant, product and calorimeter is equal to the calorimeter, means basically we are designing the system, we have in many cases, and if they are different, then I have given you the formula, no problem. So in most of the cases, Cp of products plus calorimeter is equal to the Cp of calorimeter, and it is constant for the given calorimeter, constant, right? So a little bit approximation is there, and if not, then you are also able to calculate. So this is the way through which you can calculate the delta H of any reaction, right? And if gaseous reaction is involved, then you can use you can calculate delta E for same method we are using, right? That is called bomb calorimeter, and this is called open bomb calorimeter, in which we are measuring this, because pressure is constant here, their volume is constant. So in similar steps, first step and second step, volume is constant, So work is 0 here in the first step, not required. Delta H is sufficient, right? In the similar way, everything is same. The only difference is there is constant volume and here is constant pressure. Okay, so in this way you can measure the delta H of any reaction.